Welcome back. It's time to continue to talk about these inequalities, these linear inequalities. Now, last time we talked about linear inequalities and solving, and you should be feeling pretty good about solving those. Right now, we're going to talk about something called compound linear inequalities, and here's the idea. What a compound linear inequality does is it takes two inequalities and it mashes them together. It combines them with one of two words, the word and or the word or. And we're going to talk about the differences between those two words and how that plays out and how to solve these compound inequalities. Today in this video, we're just going to get a feel for what and means and what or means with a couple examples. So we're going to start with this. Let's look at these two inequalities. This x is greater than or equal to 3, and then also the x is less than or equal to 5. And I want you to start thinking about the numbers. Some of the numbers that would work for, let's just start with this one. Think about what numbers satisfy. X being bigger than or equal to 3. Does 3 work? Does 2 work? Does 4 work? But what I mean by work is, do they make true statements? So when we're looking at x greater than or equal to 3, we know those numbers. We dealt with those in the last few videos. We know that those numbers are numbers like 3 because we have the equals. 3.1, 3.7, 4, 5, 6, 7, 8, 9, and everything to the right of that on the number line. In fact, we can graph that. We're going to in just a little bit. Now let's think about x is less than or equal to 5. Well, those numbers are 5 because we have the equals, 4, 3, 2, 1, all the decimals between those numbers and everything to the left of 5. We can also graph that, and if you remember, I hope you remember, these are set up perfect. This is awesome because we've got a variable on the left-hand side. The inequality basically points as an arrow to the right for x greater than or equal to 3. The inequality basically points as an arrow to the left for x is less than or equal to 5. We can graph both of these inequalities. And with compound inequalities, that's exactly what we do. But we graph them both at the same time on the same number line. So we're going to check that out. And after we graph them, we ask one question. We ask, are there any numbers that satisfy both this inequality and this inequality? Or we ask a different question. Are there any numbers that satisfy this inequality or this inequality? That's the nature of compound inequalities. So right now, let's discover whether or not there's some numbers that satisfy both this inequality and this one. You probably already have it. You might even be thinking of them. Well, if these are numbers bigger than 3, it's like 3, 4, 5, and these are numbers less than 5, 5, 4, 3, all the numbers between 3 and 5 should work. Like 3 itself equals. That number is bigger than or equal to 3. It's also less than 5. That should be in our solution set. We talked about solution sets, that interval of number that works. 3.1, 3.007, 4, 4.99999, even 5, but nothing beyond 5 and nothing before 3. Let's see how that works when we start graphing this. So we're going to start with x is greater than or equal to 3. We do the same thing every time. We put our number on the number line. We're going to be graphing to the right. Our variables on the left-hand side. We're thinking numbers larger than 3 are to the right of 3. Hey, it even points that way. Let's do it. Do you remember that we should be using a bracket for that? Do you remember that? Why? Why do we use a bracket for that? Well, it's got to include that number. That equal says that the number that makes the two sides equal, is also included in that solution set, and the bracket's how we represent that. Now, I'm going to use a different color pen, and the reason why I'm going to do that is because I want to show a crossover, if one exists, for the word and, which is what we're exploring right now. So we're going to go to 5. We're going to graph this inequality also. This one we just graphed was 3, and every number greater than or equal to 3. Now we're going to go to 5. We don't really have to be to scale or anything. Just make sure your numbers are in order. That really is important, especially when we're dealing with fractions. We want to know what number is to the right or left of another number. So make sure we don't get this backwards. Because if you put the 5 here, that's going to really mess things up. We don't want to do that. So make sure that we have 3, and then to the right of 3 is 5. We're counting large as we go to the right. Now, our inequality says, you know what? X being less than or equal to 5, that's going to represent all the numbers that are to the left of 5. We're going to use a bracket for the reasons that I've already talked about. Now here's the big question. Are there any numbers that satisfy both x being greater than or equal to 3 and at the same time x being less than or equal to 5? We've already talked about it. You kind of have it in your head, but look at our graph. Look what our number line tells us. When we're talking about the word and, what and means on a number line is basically and overlap. Now this is a big deal, okay? Because when we get to like graphing linear inequalities with two variables, when we're actually graphing in several videos from now, we're also going to be looking for a crossover. What the crossover represents, what this overlap represents, what the double shaded area represents are all the numbers that work, that are true, that make true statements in both inequalities. You see, when we look at our number line, all the numbers over here, before this, do you see what I'm talking about? Do you see the overlap? I'm looking for where we basically do this, like that. Not this, all right? That's for or, and we're going to get there in a little while. We're looking for crossover with the word and. So when I'm asking the question orally right now, what numbers work for both here and here, it's not the numbers less than 3. It's not this where the purple line goes forever this way. It's not the numbers more than 5. It's not the numbers that go forever to the right past 5. It's the numbers that are literally between 3 and 5. That's what and is. And says what numbers work for both inequalities, and how that works is by an overlap. This interval that's shaded with 2 colors, with 2 lines if you don't have 2 colors, but where you've gone over the same part, the same interval twice. So that's our solution set. All the numbers that work or that make true statements that are more than 3 and at the same time less than 5, got to work for both at the same time, are numbers between 3 and 5. 3, 4, 5, that's it. All the decimals between there, 3.000001, whatever, all the way up to 5 and inclusive of 5. So, well, we can still represent it, because if you know about interval notation, which I taught you a few videos ago, the interval notation still works, which means that when we're looking at our interval of working numbers, numbers that work for both, if I say the word and, are the numbers, well, where do those numbers start? It's not negative infinity anymore, because the working numbers, the numbers that are both bigger than 3 and less than 5, starts at 3 and it ends at 5. So our working interval is just here. It starts at 3, it goes double overlap, look at both overlap, it ends at 5. And we still use our brackets and our parentheses like we're used to. We still do that same exact thing. So if you have an equals associated with inequality, you're going to use a bracket, whether we're dealing with single inequalities or now compound inequalities. I'm hoping that makes sense to you. We're going to explore the or a little bit later after we deal with the and. So we'll get to it in just a bit. I'll give you one example to illustrate the concept, but we'll really hammer it in a few videos from now. So at this point, what you should be asking yourself is, do I really understand this concept of numbers that work in both? Because the numbers that work in both inequalities, that is what and means. We graph it the same exact way that we would graph a single inequality. We do interval notation the same exact way we do an individual inequality. But what happens here is we're looking for numbers that satisfy, with and at least, numbers that satisfy both inequalities at the same time. Let's look at one more. So let's say I put the word and between those two inequalities. Well, I mean, individually, those aren't so bad. We would know how to solve that, hopefully, at this point. We know how to solve this, hopefully, at this point. In the next few videos, we're going to unpack how to do that appropriately. But let's think about some numbers. Let's look at x equals 5, and let's explore what that means. So let's explore whether x equals 5 is going to be a solution or whether it's not going to be a solution. Let's plug it in, just see what happens. If we plug in or evaluate our left inequality for 5, we get 5 plus 1. Well, 5 plus 1 is going to be 6, which is clearly less than 9. That's a true statement. Now, let's plug in 5 over here. You see, when we're dealing with and, or any other compound inequality, we're considering the same number in both inequalities. That's what we're doing here. Compound means put together, join together with the two words and or or. When I join the two inequalities with and, I'm looking at this same number for both inequalities. So let's plug this in. 2 times 5 is 10. Cool. 10 minus 1 is 9. And then you ask yourself the question. 6 is less than 9. Good deal, but true. 9, is 9 larger than 8? Well, yeah, 9's more than 8. You'd rather have $9 than $8, as it says. 9's bigger than 8. That's true as well. And this is the nature of the and inequality. In order for a number like x equals 5, to be a solution. With the word and, we have to have that number being a solution to both inequalities. So we plug the same number into both inequalities, and if it's a solution to both of them, then it's a solution to the compound inequality joined with the word and. To break it down real simple, like a 10-second recap, take that number, plug it into both. If it works, cool, you got and. That's what a solution and has to do. With and, solutions must satisfy both inequalities. Must satisfy both. Let's try another number just so you can see when we don't have a solution. So right now, I'm really hoping that you guys see that this number 5 is a solution. We plugged it in, it worked. We plugged it in, it worked. So 5 would be a number that is true for both this inequality and this inequality. Let's try x equals -5. So if we plug in -5, we evaluate the inequalities for -5. Let's plug it in here. -5 plus 1, well, that's -4. And we ask, when we plugged in -5, did it make a true statement? Well, -4 is still less than 9. That's true. So we're off to a good start. But now we plug it into this inequality, and we look at it. -5 times 2, well, that's -10. -10 minus 1, well, that's -11. So -5 times 2, -10, minus 1 is -11. And then you ask the question, is -11 larger than 8? If you owe $11, is that more than having $8? And it's no, that's not a true statement. So here's what that tells us, the word and, at least, the word and. If a number, this number that we're trying to see as a solution works in one inequality but not the other, it doesn't work in both. And that's what and says. And for solutions, for in and compound inequalities, we gotta have that number work in both. So right here, hey, 5 is a solution. It works in both, this one and this one. This is not a solution. It works in one, but it does not work in the other, and says you gotta work in both. That's the idea behind and. I want you to probably take a pause for the next few seconds. Think if you try to understand what the nature of and is. If you can say it out loud, say, well, and means this. Compound inequalities with and means this. You probably have it down. If you need a little bit of help with that, what and means is you plug a number in, it's got to work for both inequalities, no matter what. If a number doesn't work for either, it's not a solution. If a number doesn't work for one of them, it's not a solution for the word and, for inequalities joined with the word and. This is not a solution. Now, let's explore or, and then we're going to be done with our video. We're going to go on and unpack and fully. I'm going to come back to or in a few videos from now. If I join these two inequalities with the word or has a different connotation in math. This was joined with the word and. What and means, I'm looking for the numbers that satisfy both, the ones bigger than 3 and the ones less than 5 at the same time. Here I want the numbers that are less than 9 on this side and at the same time greater than 8 for this inequality. And that actually works. You plug that 5 in, it's less than 9 here, it's more than 8 there. That's cool. At the same time. Or has a different connotation. Or is really kind of translates to English pretty well for us. And does as well. So when we think of, hey, I'll give you $20 if you have a car and a boat. We'll also be really good friends because I like someone who can drive and has a boat so I can go fishing. So yay! If you have both a car and a boat, you're going to come forward and I'll give you $20. You're like, hey, I win. What if you just had a car and you didn't have a boat? Would you win the $20? And you came and say, hey, I win. Give me $20. I said, do you have a car? Yeah. Do you have a boat? No. But I got a car. You're not going to have both of them. You'd lose the and game. But you'd win the or game. The or game says this. The or game says, hey, I'm going to give you $20 if you have either a car or if you have a boat. So if you come up to me and go, hey, I get $20 because I got a car. And I go, okay, do you have a boat? And you go, no, but I got a car. You go, hey, you win. It doesn't matter. I don't care if you get a boat. I want someone who can drive me to the lake, and then I want another person maybe later who can take me in a boat. But you don't have to have both to win the or game. And you had, if I said you win $20 for having a car and a boat, you'd have to have both of them. But for an or, you have to have just at least one of them. So if you came up to me, if two people came up and this guy says, I've got a boat, but not a car. This guy says, I got a car, but not a boat. They're both going to win $20. That's what or says. You got to have either or. Now there's a special case with or. What about the person who has both? So what if you have both a car and you have a boat? Well, then you also win. Or is much less restrictive than and. In order to be a solution for and, in order to win, in order to be a solution for and, you've got to satisfy both things, both inequalities, both a car and a boat at the same time. In order to win at or, in order to be a solution for or, you could satisfy both and you'd win. Or you could have one or the other and you'd still be okay, you'd still be a solution. That's how or works. So or is much less restrictive. A number has to satisfy this one or this one. So basically, it's got to be a solution to one of them or both of them. So you could have the and scenario. It's built into the or. So you could be a solution here, or even both of them. That's how or works. Let's look at a couple numbers, see whether they're going to be solutions or not. Let's start with 2. So let's plug in x equals 2. If x equals 2 here, we'd have 5 minus 4. 5 minus 4 is 1. You ask yourself the question, does that make a true statement? Is 1 less than or equal to negative 4? It's clearly not equal, but it's also not less than negative 4. Negative 4 is a negative number. It's going to be less than any positive number, not the other way around. So 1 is not less than negative 4. This is false. Let's try the other one. Let's plug in 2 over here. Well, this is 5 minus, the same exact expression. That's kind of nice. So plug in 2, 5 minus 4 is still 1. Ask the question again. Is 1 more than 4? Answer, of course, is no. This is the only case where a number is not part of the solution set for the word or. Is if that number is not in either inequality. Let me say that one more time because it's important. For or, and people get these confused a lot. That's why I'm spending so much time on this short little video here. People get this confused. This is the only time with or you don't have a solution, is if that number fails to work for either of these inequalities. For and, it must be this. It's got to satisfy both, or it's not a solution. So down here, what's true and false, that doesn't work for and. You got to be in both. For or, the only time you don't get a solution is if that number doesn't work in either one of them. For instance, let's try x equals negative 3. So if we plug in negative 3, be careful here with your signs. Please be careful. If you plug in negative 3, this is negative 6. 5 minus negative 6, well, that's 5 plus 6. That's going to be 11. Now, there is no way that 11 is less than negative 4. It's clearly false. Let's try negative 3 here. Again, same expression. So plug in negative 3. 2 times negative 3 is negative 6. 5 minus negative 6 is still 11. And yeah, 11 is larger than 4. So it satisfies that inequality of 11 being greater than or equal to 4. So 11 is bigger than 4? True. And here's the difference between and or just one more time. This is a solution. You see with or, it didn't work here, but it did work here. Numbers have to be solutions for or if they satisfy at least one inequality. It could be more. It could satisfy both. That would be a solution for the word or, compound inequality joined by the word or. But it's got to be at least one of them. So when I'm asking for, hey, if you own both a car and a boat, raise your hand, you'd have to own both of them, raise your hand. Say, if you own either a car or a boat, notice how much less restrictive that is. People who own cars are going to raise their hand. People who own boats are going to raise their hand. People who own both are going to raise their hand. That's what or says. It just takes, it says, as long as you work in at least one of them. I'm pretty non-exclusive here, okay? Just work in one. If you don't have a car or a boat, that's the only time you raise your hand. So one more time, just like a 10-second recap here, and you got to work in both. That's what it boils down to. The number has to work in both inequalities. With the word or, it's the car or the boat. You raise your hand if you have either a car or a boat or both. The only time when you wouldn't raise your hand there or win the game, if you're playing the game, would be if you don't have either. So or takes a number, plugs it into both inequalities. If you're true in one of them, you're part of the solution set for or. And takes a number, plugs into both inequalities. If you're true in both of them, that number is part of the solution set for and. That's the idea. We're going to do a few more of these. We'll go ahead and we'll start with and. We'll unpack all about that. And then we'll go on to double inequalities. And after that, we're going to talk about or, compound inequalities with the word or. The big deal here is with and, solutions have to satisfy both inequalities. With or, solutions must satisfy at least one inequality. Could be both, but at least one. That's the idea. I hope that makes sense. Get it in your head that and you gotta both, or you just have one or the other, or both. Okay, we'll see you next time for and inequalities.